Right, welcome everybody. This is my talk, Printer Hacking Adventures. No ink, no crime. So we have quite a bit of content to go through today, so let's get started. So introduction. So what to talk about? A couple months ago I was having lunch with Antrix, and he said, well, you never visited Nullcon before, you should totally come. By the way, we have a CFP, wink wink, nudge nudge. So fast forward a bit, I submitted CFP last minute. About some research I did over the past 2 years, on and off, working on printer security, mostly because I was entering the phone-to-home competition, where they nowadays have an embedded security category that also has like printers, routers, security cameras, smart speakers, all these fun things, right? So today I'll be taking you through some bugs I found and how I exploit them. So before we continue, who am I? I'm an independent security researcher from the Netherlands. Used to play and organize a lot of CTF, nowadays not so much. And I like to get code execution on everything, printers, smart speakers, servers, what have you. As long as we can get the PC control, I'm happy. So the talk outline, the agenda for today. Basically the talk is divided in two parts. First we're going to be talking about Lexmark printers. And so a bit about extracting firmware, finding and exploiting bugs. And then the second part of the talk is about Canon. And so we have a printer up on stage here, which is a Canon printer. Hopefully we'll have a live demo at some point. Yesterday I found out the live demo has some stability issues. And of course this is the last moment, so there's no time to debug it. Let's pray to the demo gods it works. I did 10 test runs and it failed once. But you know, statistics being statistics and small sample sizes being small sample sizes, that could go anywhere. And then finally we'll talk a bit about writing a debugger for this Canon printer. So Lexmark, right? The target device was a Lexmark MC322, bloody bloody blah, not very important. It uses a Marvel system on a chip with an ARM-v7 CPU, and it runs your typical Linux operating system. When you look at embedded Linux device firmware, you often find that everything runs as root and there's no privilege separation whatsoever. On Lexmark, this is not the case. There's actually privilege separation. They have systemd unit files for all the services and dependencies. There's an IPC broker that's written in Roslang. So my initial impression was I was surprised and like, yeah, this is not what you see typically on embedded Linux. So how do we get Lexmark firmware, right? So I bought a second-hand Lexmark printer of this Dutch website called Marktplaats. And it came wrapped in a smelly blanket. It was running an older firmware, and there was a write-up from CrowdStrike from previous years, Phone2Own, where they detailed their command injection bug that they found for Lexmark. So since my printer was still running an older firmware, it was vulnerable to this particular vulnerability. So I used that as a stepping stone to get a root shell on my Lexmark printer. And from there I was able to extract root file system contents. And then I was like, well, there should be code in here that's responsible for handling these firmware updates, right? So I found out there's a binary called Hydra in user bin. It's this dynamically linked binary, C++, super big, and it does a lot of things. Well, one of those things is updating the firmware and unpacking the firmware data. So the firmware data is shipped as these FLS blobs, and basically they're PJL streams. So this printer job language thing that you send over TCP port 9100. And it starts off with a small ASCII text header, has some details about this firmware blob, and then it's followed by huge encrypted high entropy data that has the actual update data. So I started reverse engineering a bit. And I found out it's split up in two regions. One is the kernel region and one is the data region. So the kernel region has like the kernel image, initial ROM disk, this sort of stuff. And then the data region has the actual root file system. And it starts with a header that is RSA encrypted. But of course the keys are inside this Hydra binary, so I was able to pull them out. So here we can see a bit of this header, and some important fields are highlighted. Most importantly, there's a size for the signature digest, there's a size for the final AES key, and the AES mode being used. And then, so I wrote a utility that can decrypt these blobs using the keys I was able to extract from the Hydra binary. And yeah, so long story short, there's a couple of headers, have RSA signature, eventually you get an AES key. And then by using my tool, you just feed it this FLS firmware update blob, and it will nicely unpack it into the kernel and data region for you that is decrypted. So nowadays, in the latest Lexmark firmware that was released in December, they've changed something, so my tool still works. But the final data partition you get has another layer of encryption on top, and it uses a hardware-derived key using some kind of TPM that's inside of the Marvel SoC. So this has not been publicly broken yet, and we won't break it during this talk, but trust me, it's coming. Just not today. So yeah, let's talk about finding bugs in Lexmark, right? So printers, complicated devices, lots of protocols, lots of parsing going on. So attack surface is huge. And I mean, we could look at, for memory corruption bugs in, for example, the PostScript interpreter stack. This is fully custom, of course. And, but this was already done by NCC Group, and they had a nice talk about this at Hack in the Box last year. And so yeah, for Lexmark today, what I did is we're going to focus on non-memory corruption bugs. So we're going to look at more logic-like things. And if you like web hacking, then you might actually enjoy the next part. So there's this standard by Microsoft. It's called WS Print, and it's basically used for submitting jobs to a printer over HTTP, encapsulated in SOAP envelopes. And part of this specification, well, there's a sub-specification called WS Event, which can be used to get event callbacks when something happens to your print job, for example. For example, the job gets cancelled, then an event is emitted, and you will get a callback. And this is all part of the Web Services Eventing Standard that was submitted to W3C committee back in 2006, so almost old enough to drink. And on Lexmark, this WS Print stuff can be reached over TCP port 65,002. So let's have a quick look at what a SOAP envelope looks like for submitting or for subscribing to these events. So in the upper right corner, you will see some XML namespaces that are shortened, and they are color-coded so you can sort of follow what's going on. And so the important thing is we have this WSA address, and we can specify a callback URL there. So whenever the event we are subscribing to, which is specified by this WSE filter thing you see near the bottom, when such an event happens, it will trigger an HTTP request to this callback URL. So again, callback URL is highlighted here, and the type of event we are subscribing to is highlighted in the bottom. So now how do we actually trigger such an event? Because like the first thing I just showed you will just subscribe to events, but now we need to trigger one. Well, we can just submit an actual print job, right? And then from a print job there will be plenty of events, and then our callback will get triggered. So we have another SOAP envelope that we use to submit a print request, and yeah, then some events will happen and our callback will get called. So yeah, so by subscribing to this job status event thing and sending a print job, we can trigger a callback. And yeah, typically you would point this to your own web service or whatever. But of course we can also point it to localhost. So now we can make the printer make a callback to itself, to maybe some daemon that normally is not externally accessible. And this way we introduce a server-side request forgery primitive. But where do we point our server-side request forgery to, right? So it turns out there's a daemon running called a Fox Service App on TCP 12039, and it's related to debugging Fox functionality. So Fox is old thing where you have a plain old telephony system and like a modem card, and You can send images to other Fox devices. Not used a lot anymore, I guess. But all these printers support it, even if they don't have actual Fox modem card in there. The daemon is still running. This is interesting. And this is a line-based protocol. So you can telnet to this daemon, and then you can issue certain commands. And so I audit this binary a bit. Most of the commands are boring. But there's one that stood out, and it's called copy file. And copy file acts like a CP command on Unix. So it takes a source path and a destination path. So, if we use this command, we can copy arbitrary files to arbitrary locations. So what does this look like if we were to try to smuggle it inside of an HTTP request? Since Fox Service App uses a line-based protocol, HTTP requests start with like get, blah, 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 and then some headers and then a body, right? It will just ignore the HTTP request because that's not valid commands for this protocol. But if we inject new lines into the path of our callback URL, we can actually smuggle commands to this daemon that's running on the printer. So, let's highlight a bit. We're sending a request to this internal daemon. We're sneaking in carriage return, followed by a normal new line. Then we have our copy file command, which is going to copy an arbitrary source to an arbitrary destination. And then, since it's an HTTP request, typically that waits for the connection to close after it gets a response from the server. But in this case, it's a daemon that's not actually an HTTP server. So we need to close the connection somehow. So we inject 2 additional commands, and that will close the connection. So now the callback will not be stuck hanging. It will actually naturally close. So we can copy arbitrary files to arbitrary locations. Seems really nice, but what do we copy? And one problem is this copy stuff is executed as a user Fox. And user Fox can do a lot in terms of writing to locations on the file system. So the other issue is we do not control any file contents. So what will we copy where to achieve what exactly? Which brings us to the next primitive. So there's a HTTP server on port 80, and it requires authentication for most of the interesting commands. Turns out there are some endpoints that do not require authentication at all. I'm not sure why. One of them is import Fox logo. Allows you to upload a file, and that file is then written to a fixed path on the disk. And I think this file is typically used for like a logo bitmap that's put on top of every Fox message you send or something. Not really important for us. What's important for us is we can now put arbitrary data on a no location on the file system. So it will always write to varfs shared Fox data logo, and the contents we can fully control. So that brings us to the next part of the chain. There's this whole crash handling infrastructure that is used whenever a daemon or service crashes to collect core dumps and some statistics, and then it will compress it and bundle it and send it to Lexmark over the cloud, so they can do like a triage of these bugs. And this thing is called auto FW debug. And so I started having a look around, and like I said, Lexmark really likes systemd. So they have systemd unit files for every service. And as part of the systemd unit recipes for this auto FW debug, there's a unit file that creates a named FIFO socket. And the path for this socket is /run svcr auto FW debug pipe. And the interesting thing is they specify a permission mask for this socket, and it's set to 666. So this means read-write for the owner, read-write for the group, and read-write for everyone else. So this seemed interesting to me, right? So we can write to this named FIFO, and then auto FW debug will pick up whatever we write there and do something with it. So let's audit auto FW debug in 1 minute. So it will start by reading from the FIFO. You can see it reads from file descriptor tree because the systemd unit specifies this named FIFO it will start with an open file descriptor to this FIFO. So you have 0 std in, then you have std out, and you have stdr. Is 2, and then file descriptor 3 will is FIFO. It's going to look for 2 semicolon separators. And it's going to string this together into a command string, and then it's going to directly pass it to system. Yeah, you should never do that, like always sanitize your user inputs, blah, blah, blah. This is like a shortened version of the main function, but it's not really that much bigger. So how can we combine all of this and use it to our advantage, right? So on the left we have a hacker. He has an exploit and he has a listener for a shell. So he's going to send a HTTP request to import Fox logo to upload our malicious payload to a fixed location on the disk. Next, he's going to subscribe to print job status events. It's like needed for the setup to trigger the server-side request forgery. Finally, he's going to send another HTTP post request which actually creates this print job. And now an event will trigger, and the printer will start attacking itself. So the WSPrint daemon will send a request, an HTTP request, to this Fox service app daemon. And then in the body is this copy command. And it will copy the Fox data logo that we uploaded earlier in the first request to this named FIFO. Yeah. And so then the payload is something like lol and then semicolon, and it just breaks out of the command that's being constructed in auto fw debug. And this leads to code execution as root. So yeah, we hacked Lexmark. Yay. Alright, like I said, it was part of one of my Ponto entries for 2022, and I was entering the competition remotely. So that means you have to submit your exploit ahead of time to the organization, and they will run it for you during the competition. And mysteriously, it failed. And so what happens after that is you go to the disclosure room with them. It's like a Zoom meeting type thing if you're entering remote. And they you discuss with them, the details about your bug, and they offer to still buy it from me, but for like a fraction of the original payout I was gonna get if I had landed the entry successfully. So I politely declined their offer, and I opted to go full irresponsible disclosure and put everything on GitHub. Just to show that how serious this is, right? And I don't like dealing with vendors, but Lexmark eventually picked up on this, and they released their own advisory for my bug chain. And it turns out that more than 100 different Lexmark printers were actually affected by this chain. So it goes to show that competitions like Ponto are nice, but if something goes wrong, then often the impact of what you potentially had is not, it's weird. Anyway, let's talk about Canon. Enough about like exploit brokers and stuff. So Canon doesn't run Linux, no embedded Linux. It runs custom real-time operating system that was made by Canon, and it's called Dry OS. And so for Canon, you can go to canon.com, and you can enter your unique serial number that's on a sticker on the printer. And then you can download a firmware updater application, and then if you unpack that application, like somewhere in there's this huge blob, and that's the firmware. And it's not encrypted. It's a custom container format. Some people figured out how this format works from Synactive, and they published some blog posts and writing and tools for this. Really nice, thank you. So we'll be focusing on the latest firmware available for this printer today. And all code and data is in this huge 80 megabyte blob. So if we unscrew some side panels from this printer, you will get access to part of the main logic board. And there's a connector there, like there's an actual connector you can plug something into, and it's the UART for this thing. So it's typical UART, 8 data bits, no parity bits, 1 stop bit, running at a slightly weird baud rate of 57600. Like typically you see like double that, I think, like 115200. But this one uses half of it. And if you connect your UART cable there, your FTDI or whatever, you get access to this debug shell, and you have all sorts of nice commands that you can use to inspect your printer. Of course, this is a physical attack, and we are trying to hack printers over the network, but it can be helpful in debugging our exploits, maybe. So, quick recap of what I did for Ponto in 2022 for Canon. There's some endpoint, not sure what it's used for. This was discovered by static analysis, and it requires, it's HTTP endpoint, and it requires basic authorization credentials. And the way basic authorization works is you have this HTTP header, starts with the word basic, followed by a base64 blob. And so this base64 blob is eventually decoded to a statically sized buffer on the stack, and the base64 decode function does not know how big the output buffer is. So you can guess what happens here. This is a typical stack-based buffer overflow. Nice thing is, Canon printers, there's no NX, there's no ASLR, really 90s stuff, but it's custom real-time operating system, so we cannot use our typical shellcode here. Top of that is a multi-core system. We have some cache coherency issues, so if we want to make a stable exploit, we have to do a bit of work. So let's look at how I exploit this bug for the Canon. So we have, first we have, of course, a bunch of A's to reach top of the stack frame, and then we overwrite the saved return address, and then we start a rob chain, right? And so the rob chain will first start with a gadget that populates R0 through till R6. And this is actually only used to get control of the LR register. And so the idea is that if we run this exploit and the rob payload is done, the printer will not crash, so it will nicely continue working like it was before. And this way we can trigger the vulnerability over and over again. And this is useful because what I did is I built this arbitrary write primitive using this rob chain. So what we'll be doing is copying our shellcode to a fixed location somewhere in DRAM, 16 bytes at a time. So you have the middle section here that's repeated 4 times. It will populate again some registers using a pop gadget. There's an address with an offset that updates all the time, and then there's a store gadget that will write these arbitrary values to this arbitrary location. And then finally, just to be nice, we end with the call to the declash flush routine that's part of the Canon firmware already. So we don't have to implement this ourselves in ROP, we just jump there with the right arguments. And this way we can copy our shellcode 16 bytes at a time to some location, and then finally, jump there. But how do we demonstrate ponage on this RTOS? Because it's not Linux. We cannot start a reverse shell or anything. There's no shell, right? So I figured the thing has an LCD screen, 800 by 48 pixels, and there's a buffer in DRAM which holds a copy of the frame buffer, so all the pixel data, and that is periodically copied to the LCD controller and then displayed on the screen. Of course, there's also UI running on the printer, and that's also drawing to the screen. So if we try to write pixels to this buffer, then the UI is also going to write pixels to this buffer, and then it's going to overwrite our pixels, right? So the first thing we do in our shellcode is we find the UI device task. Like every task has a name. So we just iterate over the first 1,000 task IDs till we find one that has the name of UI device, and then we kill it. So there will be no more UI on the device running, but now we can take over the frame buffer more easily. And so internally, the frame buffer is just stored as this linear array of pixel values. You have 1 byte for red, 1 byte for green, 1 byte for blue, repeat, repeat, repeat. So what this will look like on the floor, I don't know if we can, there's audio that you can hear. But this is a short movie from ZDI that they released after the competition. Like I said, I was entering remotely. So this guy here is running my exploit. And then, it shows a success screen. And like you can see, we took over the screen of the printer to display a nice animation. That's me giving a thumbs up. And that was it for Ponto 2022. So, Ponto next year. Similar devices, also Canon printers again. Since I looked at WS Print on Lexmark, I figured might as well look at WS Print on Canon, right? Like I said, it is standard by Microsoft, and every printer vendor wants to support this because it's a common standard, and then compatibility increases, and then hopefully your sales increase. And so I started playing around with WSPrint on Canon. And after an hour or what, and a bit of reversing and mostly just black box poking and trying random shit, I was greeted with the thing you see on the right. This exception handler that runs whenever a segmentation fault happens on the printer. And like you can see, the R4, R5, and R6, and most importantly the PC register, have been corrupted with 616161. So people who know their ASCII hex tables will know this is lowercase a. This is not uppercase a. Normally you see 4141, now we see 61. So what happened? So here's a small excerpt from a SOAP request that we sent to this WSPrint thing, right? And part of this SOAP body has this thing called WSA message ID. And so this is just a unique identifier that is then used to refer to the message at some point. I don't really know, but not that important. So this identifier goes through this parsing routine. And I have shortened it for the sake of the slides, but basically what it does is, again, a static sized array on the stack, and then there's a function called string to lower. That's my name, but I mean, that's pretty much what it does. And string to lower will iterate over all characters in the input till it finds a null byte, and then it will stop. And for every character, it will check if it's in the range of uppercase A till uppercase Z. And if that's the case, then it will add hex 20 to the character it's writing to the output buffer, because adding hex 20 lowercase is effectively. So yeah, again, you can see what the issue is here. They have like a conversion routine. It takes an input buffer, takes an output buffer, but it does not take into account the size of the output buffer. So yeah, if there's more going out, then again, we override the stack. This is slightly more painful than the other Canon exploit though. The bug looks really good at first. It's straight up buffer overflow on the stack. Lower casing could be a problem, maybe. But we're also constrained to using things that are valid within the context of an XML node's body. So we can use UTF-8 string literals, and that's about it. So why is lower casing a problem for us? If we have a look at the memory map of the DRAM for the Canon printer, we can see that all of DRAM is mapped at hex 4000 up to hex 8000. So there's 1 gigabyte of DRAM, and all the firmware text and data lives somewhere near the start right after 40B. So why is this an issue? Well, if we have an address that we want to return into using ROP, for example, and the most significant byte is 41, that's uppercase A, and this will get lowercase by the string to lower routine. So we cannot use any address that are falling in this range. This is a huge problem because all of the text from the firmware falls in this range, pretty much everything. There's a tiny bit at the start that does not, but it doesn't contain any meaningful gadgets. So if we want to do some kind of return-oriented programming, we're out of luck because we can't have these values, right? Well, that's not entirely true. I figured out that if you go to the end of DRAM and you start reading there, you actually find what's at the start of DRAM again. So there's a mirror for DRAM at address 8000. So everything you can access at 4 something, you can also access at 8 something. It's identical. It's just a mirror. Now we can actually use the things, gadgets from the firmware text and data, but just using the mirrored address. So if we change the most significant byte to 8 something, then we can access these things. But that's still some problems. Like I said, we can only use XML character entities, and we can use those to introduce certain byte sequences, but not all of them. We're constrained to the UTF-8 encoder that's used by Canon, and turns out their UTF-8 encoder is not fully compliant with the UTF-8 specification. I learned this the hard way. So if you compare it to, like, if you have Python and then you have a byte array and you UTF-8 encode it, it typically matches Canon, but it does not always match it. This took a while to figure out. So eventually I found their UTF-8 encoder, I took it out of the decompiled output, wrote like a small harness, and then I built a lookup table. For all possible values we can produce using their slightly broken UTF-8 encoder. And so, since we want to write a ROP chain, and this is a 32-bit system, we are focused on writing 32-bit values at a time in sequence for a ROP chain. And so, what we're going to be looking for gadgets that we can encode in a way that survives the uppercase to lowercase stuff, or like does not use uppercase at all. In case the most significant byte is an uppercase character, we apply the mirroring trick, and we also try things with like grouping bytes together and see if we can find UTF-8 sequences that produce these grouped things. And on the right you can see I have implemented a small encoder utility, and you can feed an arbitrary 32-bit value. And it's going to try by any means possible to find an encoding that works and survives. And yeah, some values it's impossible to encode them. If you look at the upper right, we try to encode 616 through whatever, and that's fine. It's all lowercase. You can just do it straight away. If we try to encode something that's all uppercase, it's going to fail. It's never going to work. If we try to encode something that has uppercase character as the most significant byte and then some other values as the lower bytes, it's going to apply the mirroring trick and find a way. If we encode some other value, it's going to find a way, but there will be two trailing bytes. So this is still useful. Some side effects could be potentially useful. So how do we write a ROP chain using this stuff, right? So yeah, let's have a look. It's a very tiny ROP chain. We start by popping R0 till R5. This populates a bunch of registers. Oh, let's head back a bit. So one problem, right? So what we want to do is we want to jump to our shellcode somewhere. There's another CANON proprietary protocol that allows us, I don't know what the protocol is for, but it allows us to put arbitrary data at a fixed location in memory somewhere. So this is nice. We initially invoke this, and then we have shellcode in memory at a fixed location. But it's constrained to a certain size, but it's enough to stage more shellcode later. So now with our ROP, the goal is to jump to this address. We can't directly encode this address, however, using the encoder. So in the upper right corner, you see we try to encode this address. It does not work. So I figured, well, we can do some computation using ROP, and then maybe add two values together to produce this value that we cannot use initially. So I started by simply dividing the target address by 2. And if I have like 1 plus 1 is 2, right? Turns out that dividing this address by 2 still produces an address that we cannot encode because of the encoder limitations. So then what I did is I looked at why can we encode this, and if, like you can see, it has 5-7. In this address we want to encode. The 5-7 is an uppercase character, can't use it. So simply what we do is we subtract a certain amount. Now it becomes impossible to encode it. And then for the other half we add the same amount that we subtract from the other one. So now we have two numbers that when added together will produce the address of this static buffer where our shellcode is. And both of these values can be successfully encoded using the encoder utility. So the ROP chain will just start by populating R0 till R5 with some values. We don't care what goes in R0. In R1 we put the first half of this address, and then in R2 we don't care either. R3 will contain address to another gadget that branches to R1. R4 again we don't care, and R5 will contain the second half of our address. So the two values we just computed will be in R1 and R5. Then finally we have a gadget that adds R5 to R1, producing our final address, and then it does another load multiple opcode, which pops a bunch of values into R1, R5, and R7. But that's not really important. And then eventually it will branch to R3, and since in the previous step we populated R3 with a gadget that branches to R1, we will now finally jump to our shellcode. So, we're going to try to do this live, I guess. Let's see. Oh, you can really see this thing that I have here. Can I drag it? Yeah, you can drag it. Okay, so on the right we see we're pinging this printer. Oh, but now I also have to type on the screen, that's hard. Yeah, so we will launch exploit. Oh, and yeah, like I said, we tried it a bunch of times yesterday. It worked most of the time. Sometimes it fails. I'm sorry if the live demo fails. That's what live demos do. So let's go. All right. We're going to switch to the other one. And I think we have a failure. That's great. Everybody clap for the failure. So, I guess we could try once more. Should be pretty fast to reboot this thing. Is this thing on at all? Yeah, well, it was pinging before. Oh wait, we have to unplug it. I have to wait 5 seconds. And then wait for the thing to drain fully. And replug it. Should we wait for the thing to come back? Where's my mouse? Is it booting? Not really much of anything, is it? Oh! Ah, booting. I'm sorry in advance if it will fail again, guys. Just the demo gods are not on my side today. It's not super exciting anyway. Okay, so we can see the printer is pinging us back again, replying to our ping messages. For good measure, I'm going to put the thing into standby mode. And yeah, launch it again. Switch camera. We see some blinking. And yeah, there we go. So yeah, we have custom pixels going to the screen of the Canon printer. Very exciting. All right, I'm really glad that worked the second time. I was getting a bit nervous here, I'm not gonna lie. All right, I don't know, how much time do we have left anyway? I might pass my slot already. Someone know? All right. So, real quick, building a debugger for Canon printers. Like I said, it's not a Linux printer. We cannot just attach a GDB, but it would be nice if we could just attach GDB, right? In particular, it would be nice if we could GDB in combination with Jeff. Jeff is an extension Python script for GDB. Single file Python script, you load it into GDB and it makes GDB awesome. So let's try to quickly build a debugger for Canon printers. It should do basic things like read memory, write memory, set breakpoints. So GDB uses serial protocol. Back in the days, people were actually using GDB over serial ports. That's why it's called the GDB serial protocol. It starts with a $, then there's a payload, end of a frame, and then there's a checksum. A typical session will look something like this. Debugger asks for what functionality the GDB stub supports. We'll pull the registers from the device and maybe read some memory, set a breakpoint, this sort of thing. So yeah, the way my debugger for Canon works is we upload the debugger code itself over UART. There's an MW command which allows us to poke arbitrary memory. So we use this to poke our debugger stub into memory. And then we run it, and then the first thing I will do is we'll create a new RTOS thread where our debugger is running. that will bind and listen on a TCP port and process incoming connections. So initially when you attach GDB, it will send a bogus CPU state because the printer is not actually at a breakpoint or halted anywhere, just to make GDB happy. And then, we can insert breakpoints. We're not using actual hardware breakpoints. Instead, what we're going to do is really what I call scuffed breakpoints. It's inserting relative range instructions to a dispatcher for the debugger. So the way this works, let's say we want to insert 2 breakpoints at the lines in red here. We're going to calculate 2 branch opcodes and insert them at these locations. The branch opcodes will go to dispatchers for the individual breakpoints. And in the dispatcher, you'll see it preserves R0 to the stack. Then it moves the index for the breakpoint into R0, and then it jumps to the main handler. If you pay close attention, after it jumps to the main handler, there's 2 more D words, and that contains the address of where the breakpoint occurred and the original instruction. So once you continue, press continue in GDB, the original instruction will get restored, and it will jump back to the original place, and the code will behave like normal. So I have a quick video of this, what this looks like. This thing will just sporadically reboot sometimes. Alright, so in the upper left corner we have UART output of the printer. And sorry, text is a bit tiny. Lots of shit going on. So we run a shell script that will install the debugger on the printer. And it does this by sending write commands to the UART. So you can see the UART in the upper left corner is flooded with these MW commands. This is just poking the debugger into the printer's memory. So we do not need any exploits to install the debugger, which is nice. If you want to find a new exploit, then yes. So eventually it will start the debugger, and you can see some debug messages, and it started the debugger thread, and it says goodbye. Now we're going to attach GDB to the printer. And like I said, there's a bogus CPU state on startup, so all registers contain 0. We're going to set a breakpoint at some location that's related to the bug I was just showing you before. Now we're going to run a partial copy of the exploit against the printer, and you can see on the right that GDB is actually breaking at this location. We have Jeff working, we get full context of what's happening at this breakpoint. Really nice, we can inspect registers, we can view memory, we can even do single stepping, all this sort of fun stuff. So this is a really useful tool to further speed up exploit development for Canon printers. And the code base is made in a way that should be sort of reusable, hopefully for future other projects, we'll see. And I will release it on GitHub after my talk. So some quick takeaways, no real takeaways, just I needed a takeaway slide. Printers are scary, even when you update them. The 2 bugs we talk about for Canon have still not been patched. Not sure why, what's going on there, but not my department. And like I said, the 90s bugs are still very alive. The thing with embedded security research is, usually you have to get over this initial hump where you get access to the firmware, decrypt it, actually be able to see the code, right? And once you have that part figured out, it's usually full of really stupid holes. So, yeah, if you want to try your hand at this, it's really worth it. Okay, finally, some quick greets. Other people who are hacking printers: Synactive, NCC Group, DevCore, Diary of a Research Engineer, PHP Hooligans from the Netherlands, and Muffin, yes, that's his name with many N's, and all the other printer hackers. Cooper, the guy who's sitting in the back doing all the video recordings. You're going to have a small round of applause for Cooper. Who transported this huge printer all the way to Berlin. And of course, Antrix for inviting me and the rest of the Nullcon crew. Great conference. Thanks a lot. And last but not least, my wife and kids. I love you. Thank you for your attention. You can find me on Twitter, Mastodon. I have a website, email. We're way over time, I guess. So if you have questions, it's probably better to find me after the talk or something like this.
Yeah, buy him a beer if you want to ask a question. So.
What's that?
Yeah, so they'll buy you a beer in the bar.
Oh, yeah.
So we'll go straight on to the next talk.
Right.
Thank you.
Thank you.